So the coherence length concept is clear. Is it clear? Okay. Coherence length concept is clear, correct? That means if the laser or optical source has a spectral width, then corresponding to that spectral width, right, coherence length will be decided. And it cannot, so if it is a monochromatic source of light, theoretically coherence length will be infinite. That means you will be able to see fringe pattern even if you start moving reference mirror. Right, try to imagine Michelson interferometer. You start moving reference mirror, the intensity pattern will keep on changing, 1 0 max minimum, right? It will go on. But if we are using a laser or an optical source with a spectral bandwidth of some, right, delta lambda over here in this equation, or delta nu, correct, spectral bandwidth, then depending upon the bandwidth or delta lambda, there will be, right, intensity variation for a certain length, which is approximately treated as a coherence length, and thereafter the output will become some constant value. See, this is captured it from a book, and so right, the intensity profile, right, how it changes. If the spectral width is narrow, you will see, right, intensity profile such as like this. 0 is the reference point. See, either on the right reference mirror moving away or reference mirror moving towards, both way you will be able to see, right, some intensity pattern variation, and that will look like this. However, when we are going for a spectral bandwidth, we'll see intensity variation as maxima and minima clearly distinct within a certain range. And now what I was trying to say, that different wavelengths are there, right? Lambda 1, lambda 2, lambda 3, right? It's a spectral bandwidth, light source or a laser with a bandwidth delta. That means just imagine it has multiple wavelengths. Each of this wavelength will have different right conditions for interference. It will appear. So when the path length is 0, a path length difference, right, between reference mirror and the sample mirror, all right, then exactly all these phases will be in match, right? Intensity will maximum. Then it will, as the path length changes, depending upon the wavelength, the interference intensity, means the phase angle will be different. Automatically you will see that now the intensity variation starts decreasing, and after a certain path length difference, it becomes average, some average of this, all these waves combined. Is it okay? So this is something like a burst of patterns, right, which will appear within the coherence length. The coherence length is total distance, coherence length from, let's say, this position to this position, depending upon 1 by e square of intensity and the total. However, half of that will be, right, is what we consider, right, towards one side. Okay, so that aspect is, right, clear. Is it fine? Now you will be able to. Now what's the advantage, right, of use, means what are you going to get out of this, right, this point of view? So what we will get is something like this. Of course we will see how this imaging, this OCT works, but in general, what we know, let's say light source beam is coming, it's getting divided into two arms. So this is, let's say, sample arm, this is a reference arm. Okay, it's a Michelson interferometer basically. Okay, so reference arm signal is reflected back, sample arm signal reflects back, it gets, right, a detector detects that. What detector is going to detect is the overall intensity, right, at that point. And basically this overall intensity, what it's going to detect will be depending upon from where the reflection is coming back, isn't it? So let's say this is the sample. Okay, now let's say this reference mirror is moving, so that we can find out the length of this lens. See, this is right eye lens in the eye. This is okay. This one, okay. This is you can see, no, this is the lens. Okay, what I'm doing, one light is getting focused when the light is getting reflected from the front side of this lens. Let's say this part. And if the reference mirror is exactly positioned such a way that the reference arm length and sample arm lengths are equal at that position, then what will you observe? Some reflection from the reference arm, reflection from the front part, right, post anterior of this lens will interfere, isn't it? Path lengths are equal, right, or within the coherence length. What we will see? A burst of this intensity, isn't it? As this reference arm starts moving further away or towards this, you will see that the intensity becomes average. Nothing changes much. At one point, when both reference arm and sample arms are equal, so anterior of the lens position and the reference arm is exactly, and as this starts moving, you will see burst of some intensity because that is within the coherence, right, region. You will see this burst. So correspondingly, one peak, approximate one peak over here, this central peak corresponds to one position. The position where I could capture the reflection from the sample lens, right, anterior part, right? Is it okay? Then I start moving reference arm further away like this. What will happen? Now, when my posterior part of the lens comes into it equals to the reference arm length. See, reference arm was positioned right parallel, I mean exactly with the anterior part. Now it starts moving. Then it will be equal to the posterior of this. What you will see again? A burst of, right, this. Why burst? Because within the coherence lane, the reflection from here, reflection from this lane will have constructive and destructive. That's interference depending upon, right? So you will see another burst. Yes. Is it okay? And that will give you another peak position over here. Okay. And what is this distance? Path length difference here. This is the reference position it became now. And this. So distance between anterior and posterior of this lens. Optical path length. It is not the physical distance. Although reference arm is moving physically, okay, it gives the overall, but it is n into L, isn't it? Where n is the refractive index of the lens, isn't it? Are you clear? Right? So indirectly, you could capture the information about the either that or lens size, etc., isn't it, using this approach, right? Otherwise it's not possible to capture this information unless I remove the lens and capture, right, measure. Now it is without removing the lens we can capture this information. Okay, are you all fine? Now within this lens, if there is a damage, okay, or there is something which is some let's say contaminant, impurity is there in the lens. Okay, what will you observe? How will you observe that? Did you understand how lens size can be captured initially, right? Now what I'm telling, within the lens there is some change, right? Some contaminant or some impurity. Just hypothetical. I'm just simply giving some, just for you to imagine what could be. Till you observe what is different if there is an impurity or if there is a contaminant. What is different? Fantastic, very good. If refractive index is different, then what will you observe? No, no, something simpler. So, something simpler. Reflection. If the refractive index difference comes, Fresnel reflection will be there from that, right? Are you clear? Okay, n1 minus n1 is the refractive index of the lens. Let's say it is 1 point, let's say 4. Okay, assume. Okay, little different, but 1.4. And if the contaminant has a refractive index 1 point, let's say 35. Okay, then corresponding to 1.4 and 1.35, there is an impedance mismatch. There will be a reflection, isn't it? Fresnel reflection. So now when reference mirror over here, okay, this reference mirror starts moving, first you will see the anterior, right, this position, correct, and as the reference mirror moves further, in between there will be another small burst, correct, because of the reflection from the contaminant. Small burst will come, isn't it? That corresponds to this some contaminant. Are you image, right? Then it will further move posterior part. Is it okay? That means if there is any defect, if there is any change in the characteristic of the material, it gets reflected when we are doing this imaging. Is it fine? No.
So what will happen if that tissue is absorbing more?
Okay. See, if there is an absorption, intensity will decrease, so the reflection intensity will decrease. And if the absorption is so large that everything gets absorbed, then there is no reflection, then that is the limitation of my OCT approach. I cannot use it beyond certain depth in that case, isn't it? You're clear? In case of eye, we know within the visible range, the absorption is not that much, isn't it? That's why we are seeing it very clearly, everything, isn't it? If we are going to near infrared range, around 1060 nanometer, 940, 160 nanometer also, it can pass through. However, our optical system, right, this nervous system cannot capture that way. Okay, detector is not sensitive towards that wavelength. Okay, detector, our photoreceptor is not sensitive, so we will not see the near infrared 940 nanometer, 1000 nanometer wavelength light goes in our eye, we cannot see, but it can transmit, can go till the retina easily. Okay, is it okay, right? So and the absorption is minimum. I'll show you the absorption window. Right there, the absorption goes to minimum, and that's why mostly in ophthalmology, optical coherence tomography is used with the wavelength range from 800 nanometer to 1000 nanometer, 1060, 800 nanometer. Okay, it can be used easy. Okay, is it up to 1300 also? I think it can be used, but 800 to 1000. Okay, so are you fine, clear? Now, so there are certain parameters associated with uh, uh, this OCT aspect, which decides resolution of the system. One is the coherence length, correct? It will decide the minimum size, that layer thickness that can be captured, isn't it? Are you clear? Okay, so even if the contaminant size is less than the coherence length, right, still you will measure it equivalent to the coherence length. Of course, resolution is decided by that. Okay, right, if the depth, if the, right, now second parameter is related to, so one is the right axial resolution, right, which is decided by the coherence length. Okay, coherence length will decide the axial, right, resolution. The second point is the beam size, how much we can focus, correct, so that will decide lateral resolution. Okay, so let's just try to see those aspects first. This after something 1 minute. Okay, number. Okay. So three important parameters, we'll try to see them quickly and then go forward. Okay, so okay, maybe to save the time, maybe I'll show it with this instead of okay, where is it? Okay, this okay, here, okay. This will be easy. So let's say the laser light beam, optical light beam is coming in. It get focused, isn't it? It will get focused using lens. We know how to estimate this beam waste, etc. If you can recall, we had learned. Okay, so the parameters related to that I will just okay. So one is the lateral resolution. Okay, one is lateral resolution, delta x. So delta x is this. Okay, delta x. Okay, lateral resolution. That is decided based on the beam waste, focusing spot size, beam waste. Okay, so that is decided. That is indirectly twice the beam waste. Okay, diameter. Okay, twice the beam waste. Okay, and that can be given based on okay. See, of course, I'm not deriving. We had already right learned how to estimate approximately. I'm not deriving that, but it is given by 2 lambda divided by pi into 1 upon numerical aperture. Okay, and what is numerical aperture? Numerical aperture is refractive index n through which right this beam is propagating into the beam this right beam size, radius. Okay, radius, radius of the beam. Okay, so r beam radius. Okay, beam radius divided by f. Okay, so r is beam radius. Okay, so where is beam radius? Beam radius is this. Okay, it is decided by this beam. Okay, beam radius. Then it gets focused, and when it gets focused, so right, if the r is large, numerical aperture will be large, but the focus spot size delta x will be very small. Okay, remember, n is refractive index. Okay, and f is focal length of the lens. So f is the focal length of the lens. Okay, and so in case of I, so if this is right, if we see this I, we will be able to now. Of course, this is not correct. Actually, I'm sorry. Okay, it should be. It should be like this, isn't it? The focal point is retinal point. No, where it is getting focused, isn't it? Approximately, it's around 1.67, 16.7 millimeter also, approximately. Okay, this f of the eye. Okay, right. So lateral resolution is decided by this parameter, wavelength also lambda. Okay, so shorter the wavelength, focusing will be much right. So I would prefer shorter wavelength, but there may be limitations, right? But it is right for improving the lateral resolution. Okay, one parameter. The second parameter is the axial resolution. Okay, what is axial resolution? What is axial resolution? That is not. See, that is my axial resolution will decide whether I can measure the thickness of the layer or not. But what is axial resolution? See, thickness of the layer can be 1 millimeter, but my axial resolution can be smaller than that. So that minimum. So that is what is that we have learned coherence length, LC by 2, right? Coherence length, right? LC by 2 will decide the resolution. which I say axial resolution. Okay, when I work like this means my sample mirror, these things are this side, that's it. If it is depthwise means this, correct? Along the direction of propagation of light. The axial resolution is this. Are you clear? Coherence length will decide the minimum size of the sample that can be captured. Okay, so axial resolution is LC delta Z, which is LC by 2. We already understood this in the last class. Is it okay? Are you all clear? So this is lateral resolution, this is axial resolution, right? What else plays an important role? The second, another parameter, which is the depth of focus. Okay, depth of focus. What it means? You have already learnt. Have you learnt this? Okay, and learnt? No. Depth of focus. Do you know? No? Yes, you know. Confocal parameter will decide the depth of focus. What is confocal parameter? When laser beam comes, it passes through, let's say, lens. When it gets focused, then it will get focused Gaussian beam, and then it will diverge. Then the confocal parameter decides the beam size, where approximately we can treat that beam size as collimated beam, approximately. So W, if beam waist is omega 0 or W0, it will become root 2 times of the W0. That much length is Rayleigh length, and double of that is the depth of focus. Okay, within that, whatever we measure, within that approximately it is treated as the collimated beam. Although, of course, area is changing, so intensity may be slightly changing, but so that depth of focus, so it is also known as depth of field. Okay, that depends upon confocal parameter. 2 lambda by pi W0 square, something we had, right? You had estimated, right? You had estimated in your right exam, right? So that is this, and that can also be given by this parameter. Okay, it may not have direct relevance as it is you may think, but it will decide within this length, if the beam is focused approximately within this depth of focus, you can assume that your measurements are within that, right, range. It is correct within that. Okay, so depth of focus, and if the beam is getting focused too hard, then the depth of focus will be less. Okay, too hard in the sense, if the beam's waist is too small, divergence will be large, so depth of focus may get affected. Okay, so this is one. There is one more parameter which is important. Uh, what is it? Is in case of eye. Okay, I want to see how this area, retinal, this area is. That means what I will have to do? I will have to move the laser beam or a light beam. But can it move? It cannot. No, if the lens size is small. So small lateral things we can. So in order to allow more lateral field of view, you will rotate the beam, scanning the laser beam. So that scanning will determine this basically. Is it okay? Scanning of the lens, right? So if you are designing an OCT system, now you know that if I am designing it for my ophthalmology, right, depending upon what parameters I would like to measure and capture, accordingly I will decide how the reference mirrors should move, scan, how I can adjust axial resolution, what should be my lateral resolution, what should be my lateral field of view that I should cover. The more I can cover, very good. Doctors will happy. They will, in one scan, they will capture everything, isn't it? whether I should find out, let's say, where is my lens located, right? Or shall I go and check only the retinal information? Okay, I can capture retinal information without removing the eyeball, isn't it? Okay, no, nothing to be done. Laser will take me to this, right? So there is again one more parameter which comes into picture. Can I measure using the same OCT system? Okay, with right, the same OCT system with the total depth from lens to this retina. Can I capture as it is total depth while scanning? Correct. I will see one peak anterior of the lens, second peak posterior of the lens. Thereafter, no peak, still I encounter some reflection from the retinal surface. So, third peak. If I see those peaks, I will be able to capture information, isn't it? I think I have that. Oh, I added so many things, and now I am very good. Yes, correct. So let's say light comes. It can see the cornea. Refractive index of cornea is 1.376. Right, air is 1. I'll see the reflection from here, Fresnel reflection. So I will capture cornea. Then scanning goes on. I can check now refractive index of the lens. I told you 1.40 up to 1.406, 1.37. There is one more reflection. So I'll capture anterior, then posterior, and then retina. Right? Image. Capture. Is it okay? Retina again, vitreous humor reflective, right? Refractive index is 1.336, very nearer to water, right? So approximately. So you will, whether I can capture all this in one scan, or not, right? It depends. If I'm using a time domain OCT approach, I'll tell you what it means. You already know, but I'll explain to you in terms of picture. So we will be able to capture this. But if we use, and there is another approach to even capture similar information, and that is frequency domain or spectral domain. So these two approaches are used to capture this information. Okay, so what are those approaches? So first is the time domain, let's say, approach. Okay, quickly, you already know, but once again I'll see. This is the object, okay, or a sample, right, or a sample. I want to capture various layers within this sample, correct? So what will I do? I'll move the reference mirror like this. Then from this position, I will be able to see the depth information, isn't it? I'll keep on capturing reflections. Every reflection defines one particular layer. What is that layer? I don't care at present. Okay, I just see reflection. That means there is some change in the refractive index. So each layer will give me some information about where is that layer located from the surface of this object. Is it okay? That already we learned. Okay. So this movement of the reference mirror is what it is, distance what we are moving, no? But it is capturing indirectly this time it takes, or the phase change it takes, or basically it's a time domain. Okay, see, I cannot capture very small time difference, no? So you know, in light travels at 3 into 10 to 8 meter per second. That means if it covers 30 centimeter, it is in 1 nanosecond it will cover 30 centimeter. 1 nanosecond. If I want to capture 1 micrometer length, my detector should be very fast enough to detect that small, right, pulse. That's not possible. So what is done? Same thing can be captured with the help of not measuring the time, but measuring the phase change. Okay, and indirectly, by if I change the length here, reference mirror, the phase difference is captured, which is indirectly represents the time, okay, reflection point from where it is reflecting, okay. So distance it is capturing, okay, and that distance is captured using this method. It is known as time domain approach, okay. So here the detector captures the overall intensity, right, whatever comes. So the laser bandwidth may be wide enough, right, spectral bandwidth of the light source may be wide enough. However, detector captures the total, right, intensity. So basically, if I tell you, we know based on our interferometry, right, this is the source, light source, and already you know, so nothing, this I'm just drawing Michelson standard, right, interferometry. This is, let's say, sample arm. So sample is located here, sample has various layers, and this is the reference mirror or a reference arm. And when reference mirror moves, okay, so when reference mirror moves, right, accordingly from each layer you will capture some information, okay, right, and that is being captured, and detector is measuring the total intensity, okay, of all this reflected layers, isn't it, detector. So this detector, what it measures, which we have already derived in case of a Michelson interferometer, the total intensity which detector will detect will be I from the sample arm, I from the intensity reference arm, some part of it, okay, some part will get reflected, but some part of it, plus 2 square root of I from sample arm, I from reference arm, and cosine of 2 to 2 pi by lambda z reference arm, z sample arm, whatever, right, this is, right, this is captured, okay, this is what we are capturing. So basically, the detector, okay, at different positions. Now if it is a time domain, at different position, path length difference position, okay. So path length difference is what, this is L1, so from here, this may be, let's say, L2, right, this may be at L3, this may be L4, whatever, right, this all L2 minus L1, L3, right, they are all giving path length difference, okay. And it is half of the optical path length difference. Why half? 2 times the beam traveling, no reflections there, so that is path length. So the detector intensity, right, can be given by, it is proportional to sum of total all this reflections S0, and from each layer, right, there are n number of layers, from each layer whatever is reflecting is being captured in the form of reflection, isn't it. This Zn is nothing but half of the optical path length difference, correct, path length difference between the reference mirror and sample, right, between the sample layer, right, nth layer reference mirror and the nth layer of the sample, correct, is it am I clear, okay. So this is what, this basically, correct? This difference. Are you mind clear? And this is why proportional. There will be some factors, right? Depending upon a percentage of this intensity reflected back this that. That's why proportional. So S0 is the total intensity of the light source which is reflected back to the, right. And see, this gamma factor is known as a coherence envelope. Okay, so this factor, we'll see what is time. So gamma Zn is nothing but coherence envelope. Okay, so within, what it means, within, when the path length difference is 0 between reference mirror and the particular layer, nth layer, then this factor depending upon that particular layer will get decided, and it's nothing but the intensity burst. There you will see. Okay, otherwise it will remain average. Then suddenly there is a path length equal, then again you will see the burst, and that burst is decided by this factor. Okay, so this value means this factor for Gaussian beam, it is given by the shape, okay, which is derived from here, is exponent of minus log 2 into 2Zn divided by LC. Okay, it is given by this. And the coherence envelope, okay, the coherence envelope gamma, this thing factor decreases to 0 if it decreases, gamma Zn tends to 0 as 2Zn is greater than LC. As soon as you cross the coherence length, this difference, it will go to some small amount. Okay, optical. Okay, so basically, right, and because of this you will see some small burst of intensity, and that is what I was, right, previously trying to show it to you in this graph. So this is a time domain approach. Okay, so time domain approach is, you have a broadband light source beam, this is Michelson interferometer, but to get all this Z1, Z2, Z3, Z1 corresponds to this layer, right? Z2 position, this layer, second. The third layer is Z3. If you want to capture all these three layers, you will have to move this mirror accordingly, isn't it? You start moving the mirror, you will start seeing wherever distance equal layer right, reflection, you will see the burst. You keep captured. But if you can imagine, let's say I want to see my lens right position. Now I'll have to keep observing without moving my eye till the scanning is over, isn't it? It will take some time. Scanning mirror will take some time, right? Reference mirror, while scanning, slowly and scan through. It may take few seconds, right? If I want to scan even very precisely, then it will take even longer time, right? That means it is time consuming, the process, the technique is time consuming. Secondly, if I want to scan, come back, again scan, come back, again scan, right, means, what it means, if I want to do lateral scanning, what is the meaning of lateral scanning? I want to do one position, that information, then go to next position, that information, third position, that information, let's say on the screen surface, want to do here, 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 then I'll keep on half an hour, one, then second, then third, that fourth information. It is time consuming. Okay, so those things limits my requirements, and the time domain OCT approach has a difficult situation, right? I can do it, no problem, I can do it, but it consumes a lot of time. Error may be large because of the movement of the mirror coming into picture. I can reduce that movement of the mirror by using not mechanical drives but some other drives, piezoelectric drives, etc. are available. I can use piezoelectric drive and change the position of the mirror, reference mirror. But or I can use motor, right? Motor, electric motor drive, linear drive, and change the position of the mirror. But linear drive means mechanical movement will will increase the error, but piezoelectric drive may reduce the error, but the movement will be limited to few millimeter, not very large movement you can achieve. So all these aspects as well as time taken is time domain OCT is the limit. Okay, so as to overcome this difficulty, another approach came up, which is frequency domain or spectral domain OCT. Okay, maybe today I'll close here. We'll continue the next class, spectral frequency domain, how we can capture without much of this reference mirror movement at all, we can capture at a time whole information. Okay, so that we will try to see. Okay, fine, thank you.